Welcome back, grade 11 chemistry students. We are continuing our study of intermolecular forces. And so here's where we are. There are three main types of intermolecular forces: London dispersion forces, dipole-dipole forces, hydrogen bonding forces. We last time discussed London dispersion forces, or you were introduced to London dispersion forces. We'll do more with those and more practice, of course. These flipped lessons are only meant to be an introduction. We still have to practice these skills and knowledge items, but I want to spend this flip lesson right here on dipole-dipole forces, and hydrogen bonding is going to require certainly more than one flip lesson. Let's talk about dipole-dipole forces. If you remember, we introduced the concept of a dipole in London dispersion forces, right? We introduced the concept of a dipole in physics. It is a vector quantity, which means it has magnitude and direction. How much and in what direction? And the way we do this in terms of notation in chemistry is we have an arrow with a cross where this is the positive side of the dipole and this is the negative side. The arrow points towards the negative charge. And remember also that these do not have to be complete charges. They can be partial charges, right? Because we are primarily talking about covalent bonding in all of these discussions of intermolecular forces. Because we're talking about covalent bonding, we don't have pure charge separation as you do in ionic bonding. You have partial charge separation, right? You have polar covalent bonding. But this notation still applies. We said also that the dipoles line up head to tail, head to tail, head to tail. They do that to maximize the attractive coulombic force in the system. And this, of course, is responsible for molecular properties like boiling point and melting point and other properties involving large numbers of molecules interacting. Okay? All right, now, but remember, when we talked about London dispersion forces, we were talking about instantaneous dipoles and induced dipoles. Now we're going to talk about permanent molecular dipoles with dipole-dipole forces. And these in general are stronger than the London dispersion dipoles, instantaneous and induced dipoles that you were introduced to last time. Well, what does this mean to have a permanent molecular dipole? Here are two examples. This is hydrogen chloride, and this is chloromethane. Hydrogen chloride, HCl, chloromethane, CH3Cl, both very simple covalent molecules with polar covalent bonding, which means that the hydrogen has a partial positive charge and the chlorine has a partial negative charge. Right here we have a partial positive charge on the carbon, a partial negative charge, and these permanent dipoles line up head to tail, just as they did when they were instantaneous or induced dipoles. But now these are permanent dipoles, which means that the forces are stronger because this isn't a momentary interaction. It's a permanent, full-time interaction. Okay, now what causes this charge separation to allow this picture is, of course, polar covalent bonding. And what causes polar covalent bonding? Remember? That's right, electronegativity. Differences in electronegativity of, say, between 1.8 and 0.4, and you know, this can vary depending on which textbook you access, but this is the approximate range where the difference in electronegativity between two atoms A and B is in this range, which means that the electrons are not equally shared between both atoms. There's a polarization of electrons. The electrons tend to spend more time. The bonding electrons tend to spend more time near the more electronegative atom, and that causes that polarization, that causes that partial positive charge, delta plus, delta minus. Okay, all right. So how does this work in practice? Okay, well, let's look at these two molecules. This is carbon tetrachloride, CCl4, carbon tetra 4 chloride, right? And we'll learn how to name these compounds when we do organic chemistry, which you'll probably not get to until next year. And this is the molecule chloroform, and they're very similar molecules, right? They are AX4 Vesper tetrahedral molecules. Vesper is going to come back into the picture here. The dipole moment of carbon tetrachloride is 0. That means this is a non-polar molecule. It has no dipole moment. The dipole moment of chloroform is 1.15. That's rather large. And so that means that chloroform is a polar molecule. No dipole moment, non-polar molecule. Dipole moment, polar molecule. Well, how is this possible, you might ask, right? Because carbon tetrachloride has 4 carbon-chlorine polar covalent bonds, and chloroform only has 3. You would think that the molecule with more polar covalent bonds would be more polar, but in fact it's less polar. In fact, it's non-polar. How is this possible? You have to remember that dipoles are vectors. And so what we have here in this comparison of carbon tetrachloride versus chloroform, you have to imagine that you have 4 vectors pointing at the corners of a tetrahedron. And when those 4 atoms that central carbon is bonded to are identical, as is the case in carbon tetrachloride, those 4 vectors cancel. So 4 polar covalent bonds are all pulling in basically opposite vector directions so that the net vector sum is 0. Right? Whereas if you disrupt that symmetry where one of those atoms is different, which is the case, of course, for chloroform, you have a carbon-hydrogen bond, then you have the possibility of these vectors summing to a non-zero molecular dipole moment, which is in fact what's happening. That's why chloroform has a non-zero dipole moment and is a polar molecule, and that's why carbon tetrachloride, even with an additional carbon-chlorine polar covalent bond, has no dipole moment and is a non-polar molecule. Okay. Now, what you're going to do for homework, you are going to determine whether each of these molecules has a molecular dipole moment or not. In other words, whether each of these molecules is a polar molecule or a non-polar molecule by analyzing the bonding, by looking at the electronegativity difference, and by looking at the geometry. So there's a lot going on here. All right? And you have carbon dioxide, and you have these formulas, and you're all very, very familiar with converting simple formulas like these to Lewis electron dot structures, analyzing their geometry via Vesper, but now you're doing one additional thing. You're looking at how those polar covalent bonding vectors are adding or canceling, and you're going to come to some conclusion. I'm not asking you to predict the actual dipole moment. I'm just asking you to go through this analysis and tell me whether each of these molecules is expected to be nonpolar or polar, the molecule itself, and you should also have a justification for why that's true. HL students will do SL students will do these 4. HL students will do these 6, including these 2 at the bottom here, right, which involve higher geometries that SL students are not responsible for. So that is a homework assignment, and that is pretty much all for now. And we'll see how you do with that before we go on to hydrogen bonding. Have a good evening.